Now we will start the chapter Gas Laws and Kinetic Theory of Gases. So first we'll see the properties of an ideal gas. In an ideal gas, all molecules are identical and spherical. These molecules have exactly equal coefficient of pressure and volume. The size of these molecules are very small. There is no force of interaction between these molecules. All the collision between different gas molecules are perfectly elastic in nature. When we talk about an ideal gas, there is no effect of gravity, and all the ideal gas, they strictly obey the Boyle's law, the Charles law, and the law of pressure in all conditions of pressure and temperature. Now we will go through different gas laws. So first let's see Boyle's law. Boyle's law is also called isothermal law. This law states that volume of a given mass of an ideal gas is inversely proportional to its pressure at constant absolute temperature. So according to Boyle's law, the volume of a given mass of gas is inversely proportional to the pressure at constant temperature. Here V is the volume, P is the pressure, and T is the temperature. So according to Boyle's law, PV is constant. So for a given gas, we can say that P1 V1 is equal to P2 V2, which means that suppose at any given volume V1 the pressure is P1, then this product will be equal to P2 V2, where V2 is some other volume and P2 is the pressure of gas at that volume. So this is our Boyle's law. PV is equal to constant. Now we will discuss Charles' law. Charles' law is also called isobaric law. This law states that volume of a given mass of an ideal gas is directly proportional to its absolute temperature at constant pressure. So according to Charles' law, the volume of a given mass of gas is directly proportional to its absolute temperature at constant pressure. So from here we have V by T is equal to constant. So suppose at some pressure P, if we take a volume V1 of a gas, and if the temperature is T1, then at the same pressure, if we increase the temperature, say increase it to T2, then the volume will also change. Say the volume will change to V2, then this ratio, that is V1 by T1, will be equal to V2 by T2 at constant pressure. So this is our Charles' law. Now we'll see pressure law, which is also called isochoric law. This law states that the pressure of a given mass of an ideal gas is directly proportional to its absolute temperature at constant volume. So pressure law states that pressure of a given mass of gas is directly proportional to temperature at given volume. That is, volume is constant here. So this means that P by T is constant at a given volume. So suppose at volume V, the temperature of the gas is T1 and the pressure is P1. Let's say that we have increased the pressure to P2, then its temperature will also change in such a way that P1 by T1 is equal to P2 by T2. So this is the pressure law. Now we'll see what is an ideal gas equation. From the three different gas laws that we have just seen, it is clear that pressure, volume and temperature of a given mass of an ideal gas, they are interrelated. So this relation is called ideal gas equation, and the ideal gas equation is written as PV is equal to nRT. Here P is the pressure of the gas, V is the volume of the gas, T is the temperature of the gas, N is the number of moles of gas which is in consideration, and R is the universal gas constant, and the value of R is 8.3145 joule per mole Kelvin. So first we'll see how we arrived at this ideal gas equation. So from different gas laws, that is from Boyle's law, Charles' law and pressure law, we had PV was constant, V by T was constant, and P by T was constant. This was Boyle's law, this was Charles' law, and this was pressure law. So if we combine these three equations, we'll get PV by T is constant. And the ideal gas law says that PV is equal to nRT, where P is the pressure of the gas, V is the volume of the gas, N is the number of mole, and R is the universal gas constant. And T is the temperature. The ideal gas equation is always true no matter what is the process a gas is going through. Now we will derive one more equation from the ideal gas equation. This equation states that the density, that is rho, of a gas is equal to Pm by RT, where P is the pressure of the gas, M is the molar mass of the gas, R is the universal gas constant, and T is the temperature. So we have from ideal gas equation PV is equal to nRT. So we can rewrite this equation as P by RT is equal to N by V. Now N is the number of moles of gases. Now N can be written as M by capital M, where M is the mass of the gas and capital M is its molar mass. So we can replace N here with M by M. Now M by V is nothing but mass by volume, that is density, which we represent as rho here. So we have rho by capital M is equal to P by RT, or rho is equal to Pm by RT. So the density of a given gas with the molecular mass M at a given pressure and temperature can be written as Pm by RT. Now we will see what is Avogadro hypothesis. Avogadro hypothesis states that 1 mole of each substance contains same number of particles. This number is called Avogadro number, and it is represented by N, and N is equal to 6.02 into 10 to the power 23 particles per gram mole. Now let's find out what is the number of molecules per unit volume for an ideal gas. This number is equal to P by kT, where K is Boltzmann constant and its value is equal to 1.38 into 10 to the power minus 23 joule by Kelvin. Now we will derive the formula for number density. So from gas equation we have PV is equal to nRT, or we can rewrite this equation as P by RT is equal to N by V. Now in n moles of gas there will be n into Avogadro number of molecules. So if we multiply the both side by Avogadro number, that is n, we will get Pn by RT is equal to n into n by V. Now as we said that n into n is nothing but number of molecules in n moles of gas. So the right hand side becomes our number density, that is number of molecules per unit volume of gas. Now the left hand side we have Pn by RT. Now here we can replace R by N with K, where K is Boltzmann constant. So this is our final equation for number density. As we know that K is R by N, that is 8.3 by 6.02 into 10 to the power minus 23. Sorry, 23 plus 23. So this will be 1.38 into 10 to the power minus 23 joule per Kelvin. So the formula for number density is P by kT, that is at any given pressure and temperature the number of molecules per unit volume of a gas will be equal to P by kT. Now let's see what is Dalton's law of partial pressure. This law states that the pressure exerted by a mixture of mutually inert gases is the sum of the pressure exerted by the individual gases occupying the same volume alone. So suppose that we have in a container a mixture of 3 gases. Let's say we have a container here and we have gas 1, gas 2 and gas 3. These 3 gases are mutually inert, that is they don't react with each other. So the total pressure exerted by this mixture would be sum of the pressure exerted by the individual gases occupying the same volume alone. Now let's say that the volume of this container is V and the temperature at which this mixture is kept is T. Now let's say that the number of moles of gas 1 is N1, that of gas 2 is N2 and